हेलो। चेक चेक चेक। हेलो। हाँ। कुर्सी प्लास्टिक वाला देख लो ना, कुछ आज कौन दिन है, वीरवार है ना। आज सोमवार है ना। हाँ, ज्यादा लोग आएंगे आज। चेक 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 चेक।
Good morning, sir. Okay, sir. So, in last classes, we have seen machine learning algorithms, deep learning algorithms, and the uh, recently the most used applications for generative AI, the large language model. So today we will see when we develop a model, how to evaluate that model and the different aspects like explainability. When we have a result, how we will be trust, we'll have trust to believe what the result is there. What is the reason behind this result? What are the factors? Or even in different data types and different model, the explainability comes in different way. We will see how to have faith in a AI model. And the generalizability issue, when we have limited data sets and may have different level of bias. So we have today long discussion points actually. So far we have seen our AI learning pipeline goes from, if we see from left to right, it has certain steps like data collection, the first point, then choosing the algorithm according to our objective, then model training, model evaluation and testing, and deployment, and then monitoring. So when we are doing model training, we have the data set split it as training data, test data, and external validation data sets. And depending upon these different data sets, the model is trained only on trained data, it is tested on the test data set, and then it can be validated using a separate external validation data set. That may be prospective validation data, that may be multicentric prospective validation data that was not used for model training and testing phase. So far this is clear for us. And after this model training, we need to test the we need to evaluate the model. So how we will evaluate it, there are certain metrics. So using the test data, that this training, after the training, this test data come for the model testing and the matrix is calculated. So what are the metrics and how we will see, we will now look into that. So for this classification problem, when we have machine learning model or deep learning model for classification, the very basic common model that we can use for our application is a classification. Yes or no type binary classification, or it can be multiple class classification like grading, high, low, moderate, that kind of classification. So for that, the very basic thing we know, 2 by 2 table. The left side columns is for actual and positive and negative classes. Means here we can say for patient, actual sick, actual healthy, and the top row column wise the prediction values for the diagnosed means predictive sick and the predictive healthy. So for actual sick, how many are truly predictive and how many have falsely predictive as a healthy, that will tell about the true positive and false positive. And then among the healthy, how many has been predictive truly healthy, that is true negative, and how many are falsely identified as positive among the healthy, that is true false negative. So this much I think everybody know. Still I am to cover for completion, I am telling. So after having this table, we have the true positive rate and true negative rate. This is also a quantifiable matrix. And accuracy is the formula of number of correct prediction divided by the total number of prediction. So total number of prediction means our total sample size, And the correct prediction means the true positive plus true negative. So this much is our basic understanding. And even we know sensitivity is the identifying the actually have the disease means positive plus among how many the model find means the true positive divided by this true positive and false negative. The whole denominator is the whole positive group. And sensitivity is finding the healthy, true healthy among our sample. So these two have very important application when we have screening. Objective is screening. Sensitivity must be very high. But when we have confirmatory tests like biopsy for cancer diagnostics, then healthy patient cannot be identified as a cancer patient. So here, that finding a healthy specificity must be very high. Otherwise, it will be a hazard. So depending upon our objective, sensitivity and specificity may have varied importance depending upon objectives. And then ROC curve analysis of plotting the sensitivity and specificity according to our positive thresholds and identifying the threshold. So this much already the conventional stats we know. Beside this, there are certain parameters. Precision. For AI models, precision, recall, and F1 score are the metrics that are very important to measure. What is precision? How many positive prediction made by the model are actually correct? Means it has predicted true positive, it has predicted false positive also. So among these predicted positive cases, how many are the true positive? So it is directly telling about the precision, how precisely it is identifying the positives among the identified positive. So here denominator is the false positive, and sensitivity here it was the false negative. So this is the difference in precision and sensitivity, but recall and specificity is same. Recall is the true positives. The sensitivity is same, and for precision, it is slightly different than the specificity. Means this is true negative in denominator and false positive. In precision, it is true positive and false positive. So F1 score is the balance in between these two, precision and recall. It is harmonic mean. Why the mean is not taken? Because if precision is very high, recall can be very low, and otherwise also. So a harmonic means the multiplication and then division of the this two value is taken with multiplied by 2. This is the harmonic. It is a balance between the precision and recall, and a high F1 score tells a model is very balanced for both positive and negative class identification. This is sensitivity, sir. This is same, but precision is different slightly, identifying the true classes among the predicted true. So when we tells accuracy only, it tells about the correct prediction out of all prediction, but it does not tell about the class imbalance, how the model is handling the class imbalance. For this, the all variable metrics are important. We will see with an example. If we have two class, positive class have all these blue samples and green levels are the negative level 0, it has very means 10% only data in the sample. So among this all whole sample, most of the cases are in positive level, only single cases in negative cases, negative level. So if we have accuracy 90%, means all positives are identified, but we have missed the negative. All has been identified as positive and someone are false positive also. We have not at all identified the green levels, the negative class. Then also the accuracy is 90%. So 90% is a very good value for a model performance. But here the negative classes are all wrongly predicted. So when this type of things happened, here this precision, recall, sensitivity, specificity all matters, where this false positive terms is incorporated here in denominator and numerator, and the whole idea of calculating accuracy means balancing out the true positive and true negative. So here accuracy is a not adequate thing to measure. Always we should report sensitivity, specificity, F1 score. One thing is, this is a very important for AI model performance evaluation. And after this knowledge, when we see a healthcare area, when a AI model is evaluated in healthcare area, then beyond this conventional accuracy metrics, there is certain area of transparency, explainability, and the revenue market share, means how it is applicable in our domain like healthcare, how net benefit it is giving compared to the basic standard method that is now followed, the standard method. So how it is improving our current practice and how it is adding our knowledge for decision making, the explainability component. So for that, the calibration curve is a parameter that tells about how the model is interpreting the data variability. So in this figure, we can quickly look into this. The topmost figure is showing a diagonal line, the predicted means this line is the predicted probability. And here everything is correctly predicted. The x-axis showing the predicted probability, y-axis showing the actual value, the level, class levels. So class levels may be 0 or 1, and probability, the predicted probability is in between 0 to 1 some value. So if it is more than 0.5, it will be positively predicted, positive class. And if it is 0.5 less than 0.5, then it will be negative class prediction. So top figure is showing everything is predicted correctly, but this is a hypothetical case, nothing going to be happen like this. So next figure is showing very bad model prediction. The diagonal line is the actual probability, but this orange line is the classifier, that is the probability is going too far from this diagonal line. So it is very bad model. And the lower is showing almost aligned predicted probability with this diagonal line. So this type of, when the predicted probability and actual probability lies very closely, the lines will be overlapped diagonally very close. And there is one parameter for this, Brier score. The lower the Brier score means the distance from actual probability to the predicted probability is very low. The lower the Brier score, better the model. This is one parameter for model calibration evaluation, and then the decision curve analysis, that is very important in healthcare sector. So what is decision curve? Along the x-axis, it shows the threshold probability of a person having opt for a clinical examination or some intervention or some treatment procedure or not. So x-axis showing the probability of having a treatment opting for, and y-axis showing the net benefit of different process, how the treatment is given or how the decision is made. So to some probability range in the x-axis, if we plot different models, and the y-axis shows the net benefit of choosing that process for a decision making or for a treatment optimization method or whatever the current process may be. So here, for a probability range, any probability, it can be from 0 to 1 conventionally. Here it is written in multiplied by 10, 20 means in hundreds. So within some range of probability of having a clinical decision or treatment, if we plot the net benefits across these plots, the dotted line shows the diagnostics test. The solid line is showing the model of AI generated model. Here the dotted line is the conventional test. And the intervention for all and intervention for none are that probability extremes. When we opt for that intervention or when we not at all are going to opt for the intervention. This is the standard two line for the extreme two cases. In between these two cases, there are probability of having a good result with the intervention. And all the current diagnostic standard and the AI model, everything falls in between these two probability. And when the net benefit is above the current state of the art method for the AI model, we can tell net benefit is better for the AI model. Here, the dotted line is showing the diagnostics test, the conventional process for the diagnosis, and here this continuous line is showing the AI model diagnostic accuracy. So if the net benefit is better for AI model, it will be above, means the y-axis, along the y-axis, how the model is giving the benefit that will come along the y-axis. So this plot tells about the model's applicability in clinical scenario compared to the current state of the art method. So our case, this is a very important parameter to show when we are developing an AI model, how it is beneficial or not. Yes. So when we have multiple models in our hand, like machine learning models, supervised models are many models, tree-based model, support vector machine, logistic regression, we can plot also here one by one. And we can check which model is the most beneficial. Apart from the accuracy metrics like sensitivity, specificity, area under the curve, this is also one measurement of net benefit. Holistically, how the model is going to be beneficial. So I have explained all this. So these three things are very important: net benefit calculation, clinical utility, calibration curve, how the model is truly predicting the levels, and the ROC curve means balancing between true positive and the false positives, true negative and false negative. So these is three important parameters we must report when we are developing a model. Now come to the next problem of regression. When classification is identifying a class positive or negative, regression is predicting a value for some variable. So fitting a line in between different data points and predicting for some independent variable, a dependent variable may have a new value. So this is the regression. And for a actual value, what is the predicted value? That difference is now the error. So here the prediction is not a class level. Now it is a value. So value difference from actual to predicted, it is not a kind of 0-1 difference, means probability difference. It's the actual value difference. So the metrics are mean absolute error, mean squared error, means y is the original value and yi bar is the predicted value. So how much difference is there? It is a quantitative difference measurement between two continuous value. Means predicted, if it is predicted value is 10 and actual value was 12, what is the error? Absolute error is 2. It is now like that. So all are around that difference of these two value. Root mean square error, mean square error, absolute error, R square, adjusted R2 square, all these are regression related parameters. And when we have clustering the unsupervised model for identifying phenotypes or similarity in between our data, then we are just categorizing data into certain groups. So when we are categorizing based on similarity, there are the performance metrics around this similarity factor. So within one cluster, the similarity will be very high. And in between these two clusters, the dissimilarity should be very high. So this is the basic understanding. So all accuracy metrics works around these two idea of having intra-cluster homogeneity very high and inter-cluster heterogeneity very high. Oppositely, inter-cluster homogeneity very low. So two metrics are very common. Sliots score. The B and A are the average distance between samples and all other points in the same cluster, and B is the average distance between sample and all point in the nearest cluster. So in the cluster and in between cluster, all the metrics work around these two things. And another one is Davy-Bauerlein index. That is also the distance between centroid and the average distance of point in cluster from the cluster centroid. So everything goes around the intercluster homogeneity, and intercluster homogeneity means heterogeneity. Okay. And now there is another important area of segmentation when we use deep learning for segmentation. So how we will be very sure it is delineating the proper outline when there is some tumor or pathological condition. So for this example, I have taken some from my previous study. Ground truth is drawn by an expert radiologist. Maybe you for multi-user, multi-rated, inter-rated variability, we can have two drawn ROI, and then we will have the segmentation prediction outline. So this red and blue are the ground truth from two radiologists for inter-rated variability testing, and these green and yellow outlines are the predicted outline for segmentation. So we will compare the predicted outline with the drawn actual ground truth outline. So how we will now calculate? Here is nothing like sensitivity, specificity, or nothing like clustering regression type of problem. So it's a area and overlapping things are there. How it is nicely capturing the border, and how it is the all pixels, the overlapping things are very nice. So this type of intuitive idea we must have how to evaluate this. So for this, the overlapping things comes using this Jaccard index and dice coefficient. What is this? This is the X and Y is the parameters here to calculate. X is the all pixels with coordinate values. All pixels in the ground truth area, region of interest. Y is the predicted pixels of the segmented area. So how intersection and union means? Intersection means what are the common pixels, and union means summation of all the pixels, means the superset. And intersection means the common pixels in between two segmentation. So all the formula works around these things. How the overlapping is there? If we can take the two areas, and this Hausdorff distance is about the boundary. So how the boundary is aligned with each other? Here it is one dice coefficient, and if we take this in middle example, here it is the overlapping is not very good. So it is mediocre type of accuracy, and it is very poor, 0.4. Everything below 0.5 is very poor. So these are some coefficients for the classification, means performance metrics for all these commonly used type of AI model in AI in healthcare. So mostly we will Hausdorff distance is calculated like, sir, the red line is our ground truth line. Blue is predictive. So what is the maximum distance in between these two boundary? The distance from every pixel to pixel is calculated, and the maximum distance where the difference is maximum, that is taken to measure the difference between two segmentation area, means the ground truth and the predicted. So what is the maximum difference? That tells about the accuracy level in between two boundaries. It is for image analysis for segmentation. So this was the example when we work with image segmentation using deep learning model. So this is a specific type of problem area. So for that, these are the parameters that we use: dice coefficient, Jaccard index, and Honsdorf distance. A very good question. So then you have watched it very in detail. So X and Y is the two area for predicted and ground truth. So it is union between these two for Jaccard index. And in dice, it is union, but the the intersection part is not there. So when the Jaccard index is calculated, it is slightly lower value, means the here the this true positive is coming twice in the dice. So it is giving like a in ऊपर भी है 2 TP and नीचे भी 2 TP है. So it is going to be multiplied by 2. But this effect of denominator is slightly higher level because it has another TP term. But in Jaccard index, it is only single TP term. But in the above, it is multiplied by 2. So dice coefficient, when it is calculated, it overlapping, it gives more weightage to the overlapping area. And when Jaccard index is calculated, it gives more weightage to the non-mismatch area. So if you want to understand more, you can meet me later. So how to improve AI model performance? We know clean data set. Good data set is the key thing. Then reducing bias and improving generalizability, because most of the cases we have biased data. And then selection of relevant features with explainability. This is two major things to understand the AI model, how it is, how good it is. And then fine tuning is the ongoing process. As long as we have model deployed and data is coming, prospective data is feeding into the model, and continuously it is tuned. So this is our ongoing process. But during model development, these two things, the second and third point, is very important. So now come to this. What is bias? Bias has different dimension. Training data bias, skewed data set. When we have a alignment towards some type of data, like gendered bias, like some specific type of geographical area related bias. Some disease may have very prevalent in some type of area. In northeastern side, some head and neck cancer is very prevalent. Or this type of things can happen, and the data is itself biased and we cannot eradicate it. So this type of bias is there, and for that, multicentric data collection is very important. Measurement bias. When we have a equipment, machine, imaging scanner, or some pathological data microscope to see the data, or some any kind of healthcare machine to measure the values, there may be different standard. Across different time also, the machine gets updated and the previous version is obsolete. So if we have retrospective data back in 5 or 10 years back, it may not be compatible with our current data set. So that type of bias, the data acquisition bias, is there for this historical reason. Then algorithmic bias, how the model is developed using some algorithm that we can update the model, means that deep learning model continuously it is getting updated. The weights are getting updated. So what was trained using previous version, that may not be compatible with current version. And the implementation application bias, where it was developed in US, maybe a model, deep learning model, when we use transfer learning, like it is the model is trained with large amount of data set in some country, and then it is open source, anybody can download it and they can use in on their data set. But the geographical data, the genomic phenotype, the race, different condition may be there, because we have etiology, the demographic there, the food habit, dietary habit, everything parameter can take into the place for the prediction. So that we should take our in our notice when we are using a open source data model, deep learning model, or any type of model for our case. So that is a implementation application bias, where we are doing implemented and when we are doing it in our application. So these are the different areas where bias can come. So what we can do, at least for the for this data related issue, the bias, the sample should not be biased, that we can take care. And the acquisition mechanism, the machine, that should be compatible, or there some must be some mechanism to make it compatible. This area we can take care for hospital settings when we are collecting our data. Rest of the things are not in our control. This can have some issue, but that can all this can be mitigated by technological mechanism. But for this first two things, the demographical, the area geographical bias, or some historical bias, these two things has to be mitigated in our data collection stage. So one myth is large number of data set means very good, better AI. It is not true. The data should be unbiased, clean, properly collected and documented with a standard, a common standard for all data set, for across the center or across the years. So for these points I have already discussed, like cancer genomics, the standard may change, the digital pathology variation slide in slide preparation. So all these are mechanism of handling how we handle our data set and collect the features, the parameters. So these all this I have discussed all these things. So, and the hidden clock of FLAI model, like the model lag between biomarkers discovery and clinical AI deployment in oncology around 10 years. So when we use data and develop a model, and when it comes after the model development, across centers validation, and then regulatory certification, everything, when it is completed, then only it can deploy it in hospital sectors, and it takes long time. So governments are working in this area, how to reduce the time. So the for different oncological protocol, how the treatment is given and how the response is evaluated, these are all rapidly changing. Major treatments are shifting. Uh, so since the training data has been collected, so if 5 years back some data is collected, currently if the chemotherapy protocol is changed, then everything is lost. The total data is of no use. So imaging protocol also may change. The Philips scanner gets updated. So how the images were taken using the imaging parameters, it may change. The reconstruction method of imaging may change. So all these factors are there. These are all challenging factors where healthcare data is related. So before using any AI model into our clinical practice, when it was trained, on whom it was trained, and on which clinical setting the data was collected. These three things we should assess before using any model. So these are all questions. Only accuracy, sensitivity, specificity is not an important factor. All these are very important factor when you are talking about healthcare. So mitigating bias is diverse and representative data collection that is in our hand. Continuous monitoring, human oversight, and bias detection tools, all these three things are technology dependent area. So for clinical data set, we has to be very cautious. So generalization of AI model means all type of data set, demography, variety of samples, and then model based selection is there. So for a specific type of problem, we should choose the sample wisely and we should develop the model in that sector. So the holistic approach is having a representative data, very good representative standard data. So when another thing is the overfitting, underfitting issue across all the models. So the left hand column is underfitting. It is not representing the data very nicely. Overfitting is the right column where the model is seeing the variability, each and every small variability very nicely. But when it will come into the testing phase, validation phase, it will fail. So optimal fitting is grossly generalization of the model so that it can see grossly the pattern in the data set and it can identify the proper classes or proper value accuracy in the unseen data set when it is in the validation phase. So this has to be mitigated using a more simplistic generalized model. The too simple is underfitting, too complex is overfitting. So it is good for training data set when it is overfitting, but not for the validation test data. So best is the best generalization and easy to maintain. And having across the years for all type of data having a good result. But this is very difficult to achieve due to the variability in our healthcare sector. Now come to the explainability factor. Explainability is about making AI more transparent, understandable, so that we can have more confidence in the decision it makes and better understand how it works, so that we will be acceptable for this artificial intelligence. So the skeptical thinking is common for a AI model, of course. How it is giving this result, it is kind of a black box. So two things is there. Explain AI model development cycle is the top row, is showing the upper arm of this workflow. Input data, ML model, prediction, and user interface when it is deployed. So grossly it is showing the pipeline, but in the lower arm, it is showing the XAI, means explainable AI method, explanations, and going to the deployment phase. So parallelly, when we are developing a model and doing our objective, parallelly the explainability component should be there to make our users, the domain expert or the government professionals, the regulatory board, in our case, the stakeholders, everybody will be satisfied with the model. This explainability is for trust building, improve decision making, enhance model development and bugging, and regulation compliance for the government policy. So explainability dimension is very distributed in the AI model scenario. The two idea we should understand: post hoc and ad hoc, and model specific, model agnostic. This will come with the example, the visual, conceptual, fine-grained, coarse-grained, research, end user, who are the target audience, Means these dimensions tells about how and why the explainability comes and for whom it is required. So the explainability dimensions tells the phases when it is developed. The post hoc means after the model development, ad hoc means during the model development. Explanation level, how the it is explaining, is it explaining globally or locally, means for a single data set if it is explaining, or for the whole model, and for the whole data set it is giving the uh, explanation. Model specific means when we are doing some model development, for some model methods are specific to that model, or some methods are applicable to all models. And granularity means how detailing it is giving, and the target audience. If it is data scientists, researchers, it will be differently shown. And if it is our end user, our patients, they don't know the technical terms, it should be explained in a layman language so that they can understand. So all these dimensions are around the explainable AI. So who are the user, how the it is implemented, or the for the model how it is specific or not, or how explainable ability level is there, means globally or locally. So all these factors are there in a explainable AI model. It is a vast area, but we will understand the some of it to understand when we are using or implementing or taking our research question in AI area. So for anti-hoc and post-hoc AI, anti-hoc is the explanatory is backed into the model from the start. So it is the best case scenario when from the beginning we are identifying the parameters or the explainability how the model is going to work for us. So from the beginning we are taking up the explainability parameters measurements. This is best case, but if it's not possible everywhere, post hoc is after developing the model, we can identify how model has given the output. That is kind of having a local explainable, but anti-hoc means during the model development, if we are doing it's a global, we are taking all inputs. We are doing our model development and we are seeing the output at the same time globally for all parameters, we are searching for explainability. For post hoc cases, model is developed. Now we are just identifying how the model is working. So we will give one input to the model, see the output, and that explanation will be built up on the output for that single input only. So this is a local explainability for a local only single data set when model development is over. But when the model development is in the go from step by step, then we are seeing all the variables and developing our explainability aspects for our output. Then it is a global type of explainability, seeing all the features all together, identifying the best features for our model with a statistical explanation and developing our model step by step. So this is the best thing to do, but it is not possible every time. So we do our model development first and then we show locally for an example data set how it is giving a result. So this is our basic understanding that we should have. So what I have already explained, it is written in different points. Like anti-hoc is the simple model when the decision tree, regression, rule-based system, when we can see what are the steps in decision tree, we can see what are the best parameter to take fast for the bifurcation of classes. Yes, go for negative plus, no, go for positive class, this type of segregation. So these are very fast, simple, and very good thing to have from the beginning. But when we have cases like image, audio, free text, this type of things is not possible because we don't have the features in our hand. Deep learning is handling the feature in the process like a black box. We have seen how deep learning handles image, free text, how the embedding is done, how the images are filtered. step by step to captures the different area and different features, characteristics in the image, right? We can remember that. So deep learning handles all the internal features and the importance. So this type of data is not for this. So there is limitation. So how the different methods are there? So step by step, we will see some scenarios when anti-hoc is very good, intrinsic in the model, the decision tree logistic regression. It is based for the regulated industry simple tabular data. When we have post hoc and model agnostic, means across all the model universally the method is applied, like SHAP. SHAP, we already, many of us have the idea, the Shapley feature, parameter importance and all. And LIME is for deep learning image related CNN applications, where it is universally can be applied for the models, and globally it can show the factor of the result, the prediction. Post hoc and model specific is a thing that is very targeted. For some targeted model, for exactly some application, this type of things works nicely. The GradCam will be one example. Deep learning for image classification or segmentation type of application. And then the hybrid, the mix and match is there, where the multimodal models are there. So this is an example of recently analyzed data. I will just, I will not show any detail. I will just want to show how the explainability come into the picture. The data set has multiple parameters, clinical parameters, all are tabular data. This table is showing a univariate and multivariate analysis where the decompensation means the presentation. One of the presentation is coming out to be multivariate identified probability is less than p-value 0.05, and the platelet is coming out to independently associated variable for multivariate logistic regression. So these two are conventionally, using our conventional statistical method, the most important parameter for identifying the data is for identifying the varicose bleed among pediatric patient. Now come to the SHAP-based explainability, Shapley additive explanations. The full form is. Here it prioritizes the features according to their contribution for model output. If it is classification, then the classification probability, how accurately it is giving. Individual parameter contribution is calculated with a value. The value is written in the bar plot adjacent to the bar plots. It is a comparative value for all the features, and through ascending or descending order, we can see which exact parameters sole contribution is higher for a model classification result. And this is the SHAP summary plot. This green, red and blue dot points plot that is going from positive x-axis to negative x-axis, it is representing each and every data point for this exact parameter to have the prediction. So red is high, blue is low. So if the parameter is higher, the positive means for each and every distribution of parameter, the value are showing as, every value is showing as a dot. Red value are showing as higher range of value. Blue are showing the low range of value in that parameter. So how to interpret this plot, I am telling about this. So for each and every parameter, the dots are each value. Red are higher value, blue are lower value. Red are showing positive x-axis, bluer in the negative x-axis. So when we are having the values in the positive x-axis side, it is more, means values are aligned towards positive x-axis, it is going to have a more positive, classes have the more value. So sometimes the red value means the high, means the higher probability, sorry, the not the parameter value, it is the giving the higher probability, means the positive classes, low value is the negative classes. So when the red values are towards x-axis positive side, then it is towards aligned to the positive class. Hmm. Hmm. So LSM is 20 if is, yes, if it is sir, if this high value is not for the parameter value, this high value is for probability, prediction probability. Sorry, I what I told, I mm, yes. Uh, yes, means sir, if the positive value is more aligned towards the positive class prediction, then the red will come in the positive side. If the negative value, means the lower value is more aligned towards the positive class prediction, then the blue value will be in next positive side. So how the parameter is uh, giving our means classification output, that is shown here, means if positive class have lower value or positive class have higher value in the parameter. So here variable bidding. So yes, yes, so interpretation is that only, sir, high value of LSM and yes, yes. So the interpretation is there, and above that, the top scored parameters are the most important parameter to have this prediction result. So when conventional statistics showed the decomposition platelets, yes, sir, please, clinically, please add this. Hmm.
In terms of decomposition than platelets and spleen size. So longer the bar size,
Is
that there is more association with the
Yes.
stronger is the prediction of
Yes.
this variable.
Yes.
And shorter the bar size, like for bilirubin and for sodium or for gender, so there is less prediction.
Yes, yes. So the bar height means the score is high. Bar is showing the
So it is
score
not
only.
necessarily, sir, you said that like age and ALT, it is not necessarily related to the increasing age or increasing ALT.
No, sir.
So it is not.
It is coming from this summary plot. When we are seeing this bar plot, then only bar is showing the importance factor. The value is the bar length, means the importance of the parameter. But when we are seeing this summary plot, here the interpretation is one level above. We can identify the value of parameter, how it is associated with the prediction.
Yeah,
Means
but
high value of LSM and yes.
So I understand somebody has INR which is low, this is negative reading. So the red one means high probability of not reading.
Yes, yes. So it is giving you the value oriented understanding, higher or lower value of the, means how we, after ROC curve analysis, we set a threshold and we can tell above this threshold, it is going for the positive plus, or below that threshold, it is going for the negative plus. So that type of inferencing is here. So higher value of LSM is associated with the changes in reading. Yes. Yes, yes.
But
So
with INR, sir, it is not explainable. The lower the INR, there is high. There are but less risk of varices. This is only for varices. It is not for bleeding. It is just for varices needing treatment. Means high risk
yes,
varices.
Miss Iris.
But if INR is low, then there are more chances of high risk varices. That is not explained.
So yes, this SAF summary is also used to give this type of inferencing, ma'am. Hmm. Yes, yes. So here also the topmost value, topmost parameter is the highest important parameter, and above all these things, how the value is associated with the output, that is also shown in the summary plot. It is adding another level of information. So how the values are associated. Hmm. ALT. So so if this is the case, then there is in the data set there may be lot of variation. So you can see this red and blue dots are mixed and matched, overlapped. So this variable may be very much overlapping things. Statistically, we can say in that area.
Yeah, so in this way only we can interpret. So if the red and blue are equally distributed along the zero line, so then that variable is very highly significant. But if the red and blue are mixing both sides, so then that variable may not come out to be significant.
No,
Yeah.
not
It may be
in
either.
that
It may be
way.
either. It may be either red or blue
No,
which side.
I can say that if the spread is very range of spread is very high, then the variability is high. It's not like that. We can come later to this, sir. So here I wanted to show something. The in the explainability aspect, if we take long number of parameters, and if we are with explainability, if we are taking only top 4 parameter, how the model is giving different result. So if we are taking only 4, the test AU1 ROC is 0.72 instead of taking all the parameters 0.76. So very small amount of area under the curve is reduced when we are using only 4 parameter. So using this explainable uh, aspect, we can choose very limited amount of parameters. How it is contributing to the model, that is coming out from this scoring, the importance scoring. So that this tells about how many are the most important and how less we can use. We can try for 5 or 6 also. Means we can gradually take one by one, add into our model, and we can optimize our model for a very less number of parameters, and maybe for that type of parameter that is very easily available, not associated with some difficult examination. So in that way the model can be very usable in our daily practice. So explainability factor comes there. And for the post hoc decision curve, uh, when we have a complicated tree-based algorithm, we should have the basic interpretation of how the model has given the outcome step by step. So the presentation, then LSM, whatever the value is, was the taken for yes or no purpose, don't look into this. Clinically, we should look what was the steps that it took, what was the path it took to go for the decision. It took first the presentation, and depending upon its presentation, it then saw the LSM value. Then screening Z-score. Are these parameters are clinically useful parameter when we diagnose a patient for a very high risk varicose bleed patient that need to be treated very early? So this type of understanding comes, means clinical explainability is there. If you will validate this, okay, the model is going in right direction to identify the risk factor. So these are the kind of explanation that clinicians has to give the approval, the model how it is showing. And for imaging data, if it is showing the specific area here in the lower portion, the medical image is from a COVID time, and exactly where the area of problem, the model is showing, highlighting that area. This type of explanation is given for imaging based CNN models. So I think more time is, so I have, sir, only 5 minutes maybe. Okay, sir. Thank you, sir. Thank you, sir.
यूनिवेरिएटर लॉजिस्टिक्स से भी तो हो गया था वही काम। तो लॉजिस्टिक्स में जैसे हमने 10-12 जो सिग्निफिकेंट थे उसमें से लॉजिस्टिक्स में डाल के 3-4 ही सेलेक्ट कर लिया था। तो इससे किया और उससे किया, दैट वुड बी the way to complicate things when that can be done with the simple statistics.
In that, it is integrated in the model of movement.